So it might not seem important, but inverse relations are one of the more important things you should learn. One, you should be able to learn how to unravel an equation. Let's say you have a simple line, 6x plus 5. Okay, sorry about my drawing. The first step in inverse relations is swap the x and the y. So just rewrite your equation, but where you see y, put an x, and where you see x, put a y. The next point is to get this y all alone. And to do that, that's standard algebra. One thing I like to tell students is to work from the outside in. But another thing you can look at is reverse BEDMAS. Reverse BEDMAS. Whenever you want to unravel an equation, you want to use reverse BEDMAS. So normally it would be BEDMAS would say brackets, exponents. There's none of that here. Say division and multiplication. Yes, there is right there. And then subtraction and addition, right? And I put the A in the wrong order. So reverse says we're going to look at subtraction addition first to get rid of it. And sure enough, I want to subtract 5 from each side. So I get x minus 5 is equal to 6y. And that's because these canceled out. Essentially, the plus 5 moves to the other side of the equation and it's a minus 5. And you want to remember those techniques and relationships that minuses on the right side tend to be pluses on the left side, vice versa. Multiplication tends to be division on the other side. But anyway, here, look. We're left with that. So the next step, there's no more addition, subtraction. There's just multiplication. So we got to divide this 6 away. And one thing you want to get used to is this is now a term that's tied together. So you can't just divide the x by 6. You can't just put x divided by 6. You could divide them both by 6 like that, and that's fair. Or you can put them all over the 6 like that. And of course this cancels out, and you're left with y is equal to x minus 5 over 6, which doesn't look like a line, does it? So we're going to continue and do it the way I sort of started to do it. We're going to put the x divided by 6 and minus 5 over 6. And then this here is the same as just saying 1/6 x, 1/6 times an x minus 5 over 6. And now it looks like a line because there's the slope and there's the y-intercept. Now I want you to look back at the original equation right here and notice a couple things. Notice what happened to this 5. It was a plus 5. It's now minus 5. That happens to be divided by that 6. What else happened? Look at the slope here, 6 over 1, and look at the slope down here of the inverse equation, 1 over 6. So suddenly the slopes are reciprocal. The inverse equation has a reciprocal slope. And that's important to note too. So things like that you learn along the way. Now if you're using Desmos, the best thing to do for slope is just swap the xy's in the equation like this. And it'll be able to draw it right away. Now this equation you're going to learn, this blue line, is the same as the inverse equation we just did. It's the same as x over 6. If you want 1 over 6 times x minus 5 over 6. So, oh, did I get something wrong? Yeah, it's not 1 over 6. It's, no, it should be the same. Oh, I got it wrong in the blue equation right there. I didn't rewrite the equation properly. It's 6y. There we go. Now, look, this green line here will be exactly where the blue line is. And that's because they're the same equations. I've just isolated y here, and here I've just left it unisolated. But Desmos, you'll see, can draw it very quickly if you just take the same equation and you just rewrite it with the y's and the x switched. There's a couple things I want you to also note about inverse equations. Their domains and ranges switch. Okay, so this one you can't see because the domain is forever and the range is forever. But you will see it in parabolas. But the other thing I want you to see is that they're reflected in a line y is equal to x. Y is equal to x acts like a mirror, and one graph will be perfectly reflected in that mirror to the other graph. This makes sense when you think that we're just swapping x and y values. Therefore, of course, when y is equal to x, that'll be some sort of middle point between the two of them. And It's really helpful to realize when you draw your graphs if you got it correctly, because if it looks off, you'll know, oh, I did something wrong. Let's look at a domain and range swap. Let's look at what you know about just a standard parabola. Okay. Notice the range domain of a standard parabola is XER, any x values possible, but y is equal or bigger to 0, wherever its vertex is. Now let's do the inverse, and we just swap the xy's. Okay, and look at that. All of a sudden, of the red line, the domain is x is bigger or equal to 0, and the range is any value. The y's can be any y values up and down forever. So the interesting thing to note is ranges and domains swap, and if there's a slope, there's slopes inverse or reciprocal if it's a line. You won't be able to see slope for other things, but it's an interesting thing, and you should do it with all your parent graphs. Now this is going to be a weird one though. This is going to be sine y. Yeah, look at that. It's sort of vertical version of a sine curve, right? Now let's look at a couple of others. Let's do an exponential and see what its inverse looks like. And I think you're gonna discover that to the value of y, that the reciprocal, or sorry, the inverse of a growth curve is going to turn out to be something called a log or a ln curve. So I think in this case it would be the it won't be the ln, it'll be let's use a 10, because then you'll see it perfectly. So a log curve is simply the inverse of a normal growth curve. So I'm going to do log of x. So notice my green line and my blue line are the same. So that's something come up. You haven't learned logs yet, but essentially a log curve is the inverse of an exponential, and that's because it does the reverse of what an exponential does. It asks a different question, but we'll get to that. And you should study all your. Some won't change at all, because it makes sense that if I swap x and y here, you're not going to see any difference, right? It's the same thing. And of course, some will. Desmos will get it wrong sometimes. Let's see if it gets this wrong. X is equal to the square root of y. No, it got it right. So notice that the inverse of a root function is half a parabola. If you were to do it algebraically, so you square both sides here and you get x is equal to y squared, you actually don't get the correct answer if you do it algebraically. That's what I was going to get to. Y is equal to x squared is what the algebraic solution is. It creates a parabola, of course, but in reality, the inverse of a root function is just half of a parabola. It's not the full thing, which makes sense, because the domain range has to be swapped places. You can't suddenly invent a new graph. It also makes sense that why it wouldn't be this is because when you square this, you're actually creating some negative values that don't exist in the original graph. When we do this, suddenly some negative values of x are possible that were not possible in the original graph. So there's a couple of things you got to learn about the algebra of inverse, but let's get right to the questions. Okay. It's also very useful to learn because in graphing, you must get used to why we do all this. In science, the x-axis is often called the independent variable. It's always called the independent variable, not often. Independent variable, which kind of means it's something that happens without us doing anything. It would be something like time or, what's another good thing? Maybe distance. Time's a good one, actually. And then up here, we often study something that's called the dependent variable. It depends on the independent variable. And a good example would be distance of a ball. Let's say you throw a ball. Well, time moves forward whether we throw the ball or not. But how the ball travels is dependent on how much time passes. So let's say we throw the ball up, and then gravity takes hold, and then it comes down. And interesting enough, when we're working with time, we're often never looking back in time. And we're often only concerned with quadrant 1 because anything down here is beneath the ground. But you can see that the ball parabola is very much like gravity, and we're often studying the ball based on the passage of time. But what inverse graphs let you do is they let you swap the variables. Not that you would ever measure a ball this way, but let's say time is on this graph and distance is on this one. Well, now if we know the distance of the ball off the ground, and I might have gotten that inverse wrong, but it doesn't matter, we will know how much time has elapsed. And notice that the ball has 2 instances when it has the same distance. If you go back to the original graph, well, yeah, it doesn't matter. Inverses let us study a variable by swapping their independent variables. You don't always want to do this, but let's say something like this. If I'm trying to convert Celsius from Fahrenheit, my Fahrenheit is going to be on my x-axis and my Celsius is going to be on my y-axis. But if now I'm in someone from the States coming up to Canada and I want to convert to Fahrenheit, well, now my Celsius is going to be on the independent axis and my Fahrenheit is going to be here, because I can't figure out Fahrenheit unless I know Celsius. And in this equation, I can't figure out Celsius would be here, unless I know my Fahrenheit. So I can't calculate my Celsius unless I know my Fahrenheit value. And that's the whole point, is that you're trying to predict outcomes depending on what exactly you're studying. And the reason inverse equations are really important is not only mathematically it makes you a better mathematician, but it also allows you to approach problems from different perspectives. And it's often we get trapped in high school and say, well, what's this ever going to be used for? It's not so much what it's ever going to be used for, it's how much can we improve your skills so that you can move on to the tough stuff. Because you can't get to the tough stuff unless you understand the fundamentals of mathematics. And finally, there's one thing I didn't cover. The nice thing about coordinates, just a coordinate, when you find the inverse of the coordinate, you just swap their x and y values. It's actually very easy to work with coordinates for inverse. But let's try to do as many as we can. And unfortunately, I think I have to take a break at some point in order to prepare dinner. But we're going to just look at a couple of these questions. Number 1. State the corresponding points of the inverse relationship. So looking at A, it's very easy. We just swap the x and the y. That's it. Looking at B, very easy. We just swap the x and the y. And if ever you do have points on a graph and they ask you to find the inverse graph just based on the points, you can take those points and just swap their x and the y values and then plot it on the new thing, and you will discover the inverse graph. Okay, what about C? We just swap the x and the y values. You don't change their signs or anything. You just swap them. There's C. Now, what about this? You might say, oh, how do I find the inverse of that? An inverse is written like this, I think. I think they write it as -1. Can't quite remember, but I think it's like that. So you would write it like this, which means the inverse of this thing, 2, is going to, we're going to have, when we choose 2, we're going to get a result of 1. Up here, when x is 1, y is 2. Down here, the x is 2, the y is 1. But it's the inverse relationship, and that tells us we're looking for the inverse of this function. Okay, same with this one here. The inverse of this is g. We're looking for the inverse relationship, so it's 0. G of 0 is going to yield -3 as a result. Very simple. And the last one's the same thing, the inverse relationship, which I think sometimes they just do that, but I can't remember, of 7 is going to equal 0. All right, that's fairly easy. I mean, exact values are very easy. Okay, given the domain and the range of this function, state the domain and range of the inverse function. So this is also easy. So you just take all the domains of A, B, and C, and you take all the ranges, which is going to be different, like that. And yeah, I'm just going to do range over and over again. There. Oop. They don't quite match up over here. But essentially you take all the range of the first one is going to be the domain of the inverse, and you just replace that y with the letter x. Okay? And I'm not going to do it for all of them, but you should do it. And then that means the domain of this one, becomes the range of this one. But now you replace the x with y. So I could just steal this y up here. I can't quite get to it. But you get the idea. Because domain's always x values and range is always y's. So there you go. In this case, because they both had xer and yer, nothing changed. Nothing changed. But on the next one, whereas y was er, that means the new one x is er is the domain. That's the domain. So I'm just going to copy this domain here because it's already there. And then the range switched here. This was the domain of the other one, but that is now the range of the inverse. So domains and ranges switch. And then don't forget you put the y there. And you just keep doing that. It's pretty easy. So this was the range of the original one, which will now become the domain, except I have to put, I have to use xer. There we go. And I have to use the letter x in this one. And whatever the domain was in this one will now become the range in this one. And you just got to remember that you're going to use x, y, er. And over here, yeah, see, I forgot to change these two x's. But it still works. And I can't quite grab it. Let's see if I can grab it now. Yeah, there we go. That y and there, that y. And finally, the last one. This was its range, so now it becomes its domain, and you got to change all those y's. And this was the domain, so on the inverse, it will become the range. And don't forget to change those x's to y. So all ranges and domains swap. And for straight lines, they'll become, the slopes will be reciprocal too. Now, finding the inverse of these is easy because the inverse of line is going to be a line. So right away I can say, okay, this one matches to D. This question says find the inverse find the inverse of A of these graphs based on, here we'll read it. It says match the inverse relation to their corresponding function. There's 6 of them. So that's the top with the, I think it's the top with the bottom. It won't matter because you'll still be able to match it. But anyway, the inverse of a line is always a line. So the only one that can match with are these two. All right. This here is a parabola. So the inverse of it is going to be right there, parabola. And actually, probably more likely that this is, yeah, anyway, it doesn't matter. This is doesn't look like a growth curve, but it's probably the top part of a growth curve, which means that one. Now, if in doubt, you can find an exact value. You see this one? This is minus 4 comma 0, and you should be able to find that if you swap it to 0 comma minus 4. You should be able to find it on the, sorry, that's 4 comma 0. So if you swap it 0 comma 4, there it is. All the dots on this graph should swap. You should be able to swap the x, y, and find them. So if in doubt, like look at here, this is minus 3 comma 0, so we should find 0 comma minus 3. And there it is there. And that's how you can make sure. For instance, it crosses the line right here at 0 comma 9. So right here at 9 comma 0. So you can just make sure those dots indeed, when you switch them, match. This I just knew visually. So a good example here, the vertex of this here is at 0, 2. So at 2, 0, there we go. We should find the inverse. And that's pretty much how you can match. Matching graphs is actually quite easy. You just have to look for specific points and see if they exist on the other one. But you also have to just fiddle around. Like I say, take Desmos and learn to spot what the inverses are going to look like. I mean, a parabola's inverse is going to be lying flat on the ground. And a square root function is going to be half a parabola standing up. A growth function is going to become that sort of log curve. A sine inverse is going to go upwards. So it's the same with a cosine. Rationals are harder to spot. Consider this function. Find the ordered pair on the function. Now that's a really confusing way of saying it right there. That's super confusing. It's saying find Find the y value when x is 4. That's all this is saying, and it's a really confusing way of saying it. So when we put 4 in here, 4 cubed is 64, times 2 is 128, plus 1 is 129. So that means we get 4, comma, 129 is the ordered pair when x is 4. Find the ordered pair of the inverse relationship that corresponds to that one you've just found. Quite simple. We swap the x and the y values. So it's 129, comma, 4. Find the domain and range of f. Well, this is a cubic. Cubics go like this. Their domains go on forever, and their ranges go on forever. So that means the same is true for the domain and range of the inverse. So there's no need to do it. The plus 1 just elevates the inverse, the cubic up by 1, but doesn't change its domain and range. And then, is the inverse relation a function? Please explain. Okay, so when we turn this in sideways, we will get something like this. And right at this point, it is not a function because it won't pass the vertical line test. And there's ways of proving it, but you essentially have to realize what happens when you take a cubic, which is a function, and reverse it. That spot right here, pretty much at 0, 0, it won't pass the vertical line test. Okay. And I'm just going to try something here. Cube root. No. Yeah, I forget. Oh, I know how to do it. So it will be x to the power of a third. There we go. There's the inverse. Now I was just going to try to find the derivative. Okay, yeah. Right at the 0 mark, there's no possible. It cannot exist. It cannot pass the vertical line test. And you learn that in derivatives in calculus, why it can't. Because essentially, g of 0 is undefined, which means it's too vertical. It can't be a function. Visually, you get an idea for it, but there's ways of proving it as well that's not covered in this course. Repeat question 4 for this function. So they want us to do it again, but for this function. First of all, spot your function, define your function. That's a cubic, and cubics are a little bit different. So let's just do x to the 4. I think it was plus 8, right? And we'll get rid of the blue line. Minus 8. Okay. All right. So that looks like that. It should have a W feature. Yeah, you can't quite see it, but some of them look like W's down here. And cubics start off in quadrant 1 and end in quadrant 2, and they're start in quadrant 2, end in quadrant 1, and they have a vertex. They're dictated by this vertex, so the lowest point will be there, which means its range is limited. Its range is limited. Okay. There we go. And then if we're going to find 4, f of 4 for this, we would put 4 in there, and 4 to the power of 4 is 256, and then minus 8 is 248, which means on this graph we'll find 4, 248. And you can always make sure by going to Desmos and doing it proper function notation. And then Desmos will calculate f of 4 for you, 248. And so that's way up off the graph, right? It's way up there. And you can also label as well. You can have it identify it. But in this case, it doesn't matter. Which means the inverse point will be at 248, 4. Now, to prove this, I can just draw my, let Desmos draw my inverse for me. And you'll discover, sure enough, this falls right on the inverse. Can't quite get it because I'm not zoomed in enough. There it is. Now also, notice, especially if I draw the y is equal to x mirror line, it's the inverse perfectly of the green graph, which means their domains and range switch. Since the domain of the first green one is xer and the range is y must be bigger equal to 8, that means the domain of the red graph is x must be bigger or equal to 8, and the range is unlimited. And sure enough, when you zoom in here, you'll discover the vertex of this one is indeed the opposite of the vertex of that one. So they all follow that pattern for inverses. It does get more complicated when you hit higher levels. So we found the ordered pair of this new one and the inverse. We found the domain and range. And we found the domain and range of the inverse. Is the inverse a function? No. You can see that x is equal to a. Let's see if it'll let me do it. It won't let me. Will you not let me create a slider? Let's see if it'll. Yeah, there we go. The red line won't pass the vertical line test, but the green one will. So the inverse is not a function in this case, and neither of them was. Okay, so I just kind of left it running. Graph each of these functions and then their inverse, I believe it wants you to do, on the same set of graph paper. So I'm not going to graph too many, but learn to recognize what's the first graph, what's the first function. It's a parabola. It looks like that. What's the inverse going to look like? It's going to look like that. So is the inverse going to be a function? No, it's not. What's this one? Sine of x, and it goes between minus 360 and 360. So it's going to look like that. It's only going to have 2 periods. What's the inverse going to look like? It's going to look like that. And it was not a function. What is this? This is a line. It's y is equal to minus 1x, essentially. So that means it's a line going down, and the inverse will be a line going that way. And both are functions. So just know your functions. What's that? That's an absolute value, right? And the absolute value will look like that. So what will its inverse look like? It'll look like this. So they will, that is not a function. So you can see for inverse functions, no, no, and no. Only that one, the line is. For sketching it, well, know that this graph here, the vertex is 0, 1. So the vertex of the inverse is going to be 1, 0. Notice that the range of this is y is bigger or equal to 1, which means the domain of this one is x or bigger or equal to 1. And of course, you can always let Desmos do it for you. So there you go. There's the domain of the vertex of this one, and here's the vertex of that one. Desmos is a far faster tool for understanding these things. That's why I encourage everyone to do it. So let's do it for sine x. Here's sine x. And here's the reverse of sine x. Right? And even if it's sine x for 2 periods, well, you can limit the range and vertex by doing this. And I think it might not accept 360 because we're working in radians. Oh, it did. And yeah, it's working in radians. So let's see if it will accept minus 2 pi. Yeah, it did. And we'll get to radians soon. And in this one, the range is limited, so it's harder to dictate. And I don't think I can do it without actually coming up with the formula for it. There is a formula for it where you can do y is equal to sine to the power, I think it's negative 1x. Sort of got it, not quite. Anyway, Desmos is a far faster tool for these. And here's the y is equal to minus x. And here's the x is equal to minus y, which becomes the same as, yeah, it becomes, oh, that was interesting, actually. It becomes the same as y is equal to, oh, actually, you know what? Sorry, my bad. The inverse of this thing, because it's a perfect line through negative x, when you mirror it, remember that we're mirroring through the mirror y is equal to x, when you mirror it, it mirrors back right onto itself. So my bad on that one. The inverse of negative 1x is still y is equal to negative 1x. It's one of the few times the inverse will just fall back on itself. And then the last example was absolute value, x plus 1, right? And they did this so that you could see the vertex change. There. There's that vertex and there's that vertex. They swapped, and here's the mirror. So they've mirrored perfectly through that. And you should be able to, if ever in doubt, if you know 5 coordinate points, that's where studying your main graphs are important. If you know 5 coordinate points on your parent function, you can just swap those coordinates and map it out, and then connect all those dots, and you'll verify that you got the inverse correct or not. Question 7. Oh, here's the example I was talking about. So here's the formula for converting Celsius into Fahrenheit, and you see that its F is equal to something, which means that the F would go on the y-axis up here, and the Celsius, would go on the independent axis. So if we know this, we can figure out F, and it's simply multiplying Celsius by 9/5 and then adding 32, which makes sense because when Celsius is 0, freezing point, we know that Fahrenheit is 32. Can be used to convert Celsius into temperature. Find the inverse of this relationship. Describe what it can be used for. Well, of course, it can be used to convert Fahrenheit into Celsius. Use the equation to convert 20 degrees Celsius to its equivalent Fahrenheit, and then use the inverse to convert it back. Probably get some, might get, no, actually you won't get any error on that. So first let's work on the formula, and let's, instead of F, say Y, and instead of C, say X. So here's the original formula. And if we wanted to figure out 20 degrees, it's 20 degrees divided by 5, so that's 4, times 8, 36, plus 32. 36 plus 32 is 68, which means 20 degrees Celsius, which is room temperature, is 68 degrees Fahrenheit. And actually, I don't think it's degrees Fahrenheit, isn't it? It's just Fahrenheit. And now let's find the inverse. Well, the first step, what's the first step? You've got to swap the x and the y's in your equation. And actually, I'd rather spend a lot of time doing inverses. So let's start by swapping the x and the y. So I'm going to put the x where I see the y, 9/5, and the y where I see the x. So that's step 1. And then step 2 is isolating y based on reversed bed mass. Well, right now, or you could tell the story of y. What happened to y? 1, y got multiplied by 9. 2, y got divided by 5. 3, 32 was added. So that's in bed mass order. So here's why I say reverse bed mass order. Let's reverse those steps. 1, we have to subtract 32. 2, we have to multiply by 5. And 3, we have to divide by 9. Which makes sense. It's the same thing as reverse bed mass. So our first step is subtracting 32 from both sides, which means I'm left with x minus 32 on the left side, x minus 32 on the left side, equals 9/5y. So what does our next step right here say? It says multiply both sides by 5. So I'm going to multiply both sides by 5. And remember to put this in brackets because the 5 must multiply both things. These cancel out. We get 5x minus 160 is equal to 9y, right? That makes sense. And then finally, step 3 of reverse bed mass is we have to divide everything by 9. So again, the important thing, put this in brackets, divide it by 9, and divide this by 9. So this is going to cancel out, and we're left with y is equal to 5/9x minus, what's 160 divided by 5? Or sorry, by 9. 160, and I don't think it's going to, and you never want to use this decimal because it's going to produce inaccuracies. So instead you got to say, well, it's minus 17, and what's left over? What's 9 times 17? 9 times 17 is 153, so it's 7/9 left over. 17 and 7/9. The reason you don't want to round up like that, let me make sure I got all this right. Yeah, I got it right. The reason you don't want to round this down or decimalize it is because you lose accuracy, which is I think what they're trying to get to now. So now they're asking us to find the temperature we got in Fahrenheit, plug it in for X, and see if we get the same 20 degrees. And I bet what we'll get is rounding error. So we're going to take 68. We're going to multiply it times 5. And we're going to divide it by 9. Yeah, and see we get this crazy thing. And then we're going to subtract. And we might as well subtract 160 divided by 9. Yeah, we get 20. So we didn't get rounding error because the 0.777s cancel each other out. So now that's the inverse equation. If we were to write it in the use of Fahrenheit, we'd get C is equal to 5/9 of your Fahrenheit figures minus 160 over 9. So that would be the formula for converting Fahrenheit into Celsius. And you will get rounding errors if you're not careful. But the value of this is we now have a formula we can use to convert if ever we travel into a country that uses Fahrenheit and we're used to Celsius. And I know it's a simplified example, but the point is that you'll need these skills as a mathematician, engineer, or whatever to do these sort of things. So here we have a very familiar area. What is that? Area is pi r squared. Well, they're talking about a circle. It's convenient for calculating the area of a circle when the radius is known. Find the inverse. Okay. First of all, let's rewrite a is equal to pi r squared as y is equal to pi x squared. Y is equal to pi x squared. And forgive my use of pi. I don't have an easy symbol here. And then next we're going to swap our x and our y. So we get pi is equal to y squared. And now we've got a reverse BEDMAS here to solve it. Well, in reverse BEDMAS we have brackets. We don't have any. Exponents. And then we have multiplication division. So what's happening to my y here? Well, it's definitely got an exponent, but it's being multiplied by what? By pi. So our first step in reverse BEDMAS is divide both sides by pi. So you're getting y, you're left with y squared is equal to x over pi. And then when we square root both sides, and since we're only working with area, we're only going to need positives. So when we square root both sides, we get y. Normally we'd add a plus minus here, but because we're working in area, everything's positive. The square root of x divided by pi. Now we've got to replace our x's and y's back to what our new things are, and that is radius is equal to the square root of, and I'm just going to write in brackets, our area divided by pi. Which means if I know the area of a circle is 100, I can take 100, whatever it is, meters squared, let's say, and I can divide it by my pi, and I'm going to get that, 31, and then I can take the square root of it, and I will know my radius is 5.64 meters. So for a 100 meter squared thing, I know that my radius will be 5.666. So kind of, you might say that's kind of useless, except that you will find real life applications where you know the area of something and you need to find out some dimension of it. Or often what you're trying to do in construction, for instance, is you're trying to figure out what's the least amount of material I can use to build an object that gives me the biggest amount of space, like an apartment building. And ideally, circles will give you more use of volume than squares do. But squares, we don't divide land by circles. We divide them by squares. So you're often forced as an architect or engineer to look for what's called optimized use of space. Use the equation given in part 1 to calculate the area of a circle with a radius of 5. Okay, well, 5 squared is 25, so the area is 25 pi. I'm just going to leave it as 25 pi meters squared, which is roughly, 78 something meters squared. And then express the area in exact value in terms of pi. There we go, 25 pi. Use the inverse relation to calculate the radius of the circle of the area you just calculated. Okay, well, radius is equal to the square root, and I said 25 pi divided by pi. So sure enough, they cancel out. So radius is equal to square root of 25, which means my radius is 5. Normally you'd say plus or minus 5, except that we're only working in dimensions, and dimensions are always positive. So you can see that the inverse equation helped me figure out the radius if I knew the area. You might, again, not see the utility of this, but I actually feel that learning how to inverse equations is incredibly useful for a lot of real-time things. Given the function, find... Okay, this is interesting. So if I find all my x values of this, all my x, y values for this, given 3, 9, and 9 minus 3, and 9 minus 3 here, and then they ask me to find the inverse, well, for instance, if I know there's something comma 3 over here, then I know that the inverse value. But let's just do it. Let's do it long way. So it's asking me to find h of 3. 2 times 3 plus 7. h of 3 is 13. h of 9, 2 times 9 is 18, plus 7 is 25. So h of 9 is 25. What's 25 minus 13 divided by 6? 25 minus 13 is 12 divided by 6 is 2. And by the way, what is that? What did they actually give us there? That's actually the slope of, since this is a line, we ended up calculating the slope here, because this is the, if you look very carefully, this is the y value of the x of 9, and this is the y value of the x of 3. And you're essentially doing delta y up top and delta x at the bottom, and that is slope. So we just calculated slope, and we found out it's 2, which makes sense because there's a 2 right here in front of the x, which I'm going to tell you right now as a guess, the slope of the inverse is going to be the reciprocal, 1 over 2. But let's work at that. We can't find this unless we either find the inverse equation or put the 3 right there, and that's another tip that you can do. If we're going to find the inverse, they're essentially the inverse, that's going to be the y value of my regular thing. But anyway, let's just find the inverse equation first. So we start with y is equal to 2x plus 7 is the original equation. Then we swap our x and our y. And see if you can see what I'm doing. And then we're trying to get y all alone. So I get 2y is equal to x minus 7. What did I do there? I subtracted 7 from both sides. So I got 2y is equal to x minus 7. So I divide both sides by 2. I get y is equal to x divided by, let's just put x minus 7 in brackets, divided by 2. And then I can rewrite it as x over 2 minus 7 over 2. So that's now my new inverse formula, and I can write it as h inverse of x, which just means the inverse of this formula here is a half x, there's the slope right there, minus 7 over 2. So there's the inverse formula. Notice some relationships. This was plus 7, now it's minus 7, and that divided by 2 is the division of the original slope. And notice that this slope is the inverse of that one, reciprocal of that one rather. So now let's calculate what's the h negative 3. So when x is 3, I get 3 over 2 minus 7 over 2, which is minus 4 over 2, which is minus 2. And 9 is half of 9, which is 9 over 2, minus 7 over 2, which is 2 over 2, which is 1. And so when I calculate it, what's 1 minus minus 2? That's 3. What's 9 divided by 6? It's a 3, it's 6, which is half. All we did again for this one is calculate slope, because that's the y of that x, and that's the y of that x, and that's delta y over delta x. And it makes sense. There's the slope, and there's the slope. And there's the slope, and there's the slope. So you're going to find these interesting relationships, and they're very useful. I'm surprised there wasn't a follow-up of what do you think that last thing means. Oh, and I missed one. I missed 9. Does it ask that? No, it doesn't. So let's do 9. Okay, I'm going to do 9. This is just an interesting test of your algebraic skills, and you might think, I don't want my algebraic skills, but the more you do algebra, the easier it gets. The easier it gets, the higher your marks, the more you get confident, the more you get confident in all things, in all parts of life. And I often tell students, if you can get good at a subject that you don't particularly like, it means that you can get good at anything. So here we are, we're giving a basic formula where we don't know k. And then we're given the inverse for the inverse formula, when x is 15, y is 2. Well, what do we know about that? Well, they've given us 15 comma 2 as a valid point on this inverse graph. 15 comma 2 is a valid point, which means the inverse point exists on this graph over here. This is an x where this was a y on this inverse, and this is a y where this was an x on that inverse. It must be, which means since this x is 2, it means that f of 2 is equal to 15. Okay, that's interesting. Which means if I rewrite this first equation in terms of y, this first equation is y is equal to kx cubed minus 1, but I have a valid y and I have a valid x, which means I can rewrite it as 15 is equal to k 2 cubed minus 1. What's 2 cubed? It's 8, so I get 15 is equal to 8k, the missing variable, minus 1. Now I'm just trying to get k all alone, so I add 1 to both sides. And I get 16 is equal to 8k, and now I got to divide by 8 on both sides. And I get k is 2. And if in doubt, you can go back and take 2 and test it out and say, does 2 work in this? And if I find the inverse equation, do I get f15 is equal to 2 in this? And you will find that indeed f of x is equal to 2x cubed minus 1 is the correct equation. Let's plug a 2 in there. 8 times 2, 16 minus 1, 15. So we do and get 2 comma 15 as a result, which means this inverse dot is accurate. Very helpful to start thinking in deeper interpretations, because teachers love to throw in missing variables like that and then give you two equations to solve it. Whenever you're missing 2 variables, you need 2 separate equations. When you're missing 3 variables, you need 3 separate equations. When you're missing 4 variables, you need 4 separate equations. Suppose that the variable a represents a particular student and f of a represents the student's overall average in all their subjects. Is the inverse relationship of f a function? Not if they got the same mark for all their subjects. So for instance, a represents Ted, and f of Ted is his average. And then if we inverse it, this is the average. Are we going to get Ted out of it? Well, let's say his overall average. Will it be a straight line on his overall average, or will it, if it's a vertical line, for instance, then the inverse would be a relationship. This wouldn't. It's a good question. It depends if the inverse creates a vertical line situation, right? So if he got the same mark twice, I believe it would foul it up. It's interesting. I got to start copying the answers. I don't like those questions because I like just working on number questions, but I get the appeal. I just don't know if it's... I think they should have found a better example. Determine the inverse of each equation. Well, start by rewriting the equations in terms of x and y. Then swap the x's and y's. I'm doing the first one. Then use reverse BEDMAS to get this y all alone. See if you can see what I did here. What did I do there? I subtracted 4 from both sides. See, I subtracted 4 from both sides. Now what do I got to do to this to get y alone? I got to divide both sides by 3. So I get y is equal to 1/3 x. How did I come up with that? Because it's x divided by 3 minus 4 over 3. How did I come up with that? Because it's minus 4 over 3. You're allowed to break this fraction up into two separate fractions. So that's the inverse. Notice that the slope of this line is 3, and the inverse slope is the reciprocal. We had this one already. The inverse of b is the same thing. So if we rewrite it of b, I'm doing b now right here. If I rewrite it in terms of, so if I swap my x's and y's, and then I've got to get plus y all on its own, so I have to divide by minus 1 on each side, because you always want a positive y. And lo and behold, I get the same thing. And that's one of those cases where the inverse happens to mirror precisely onto itself. Okay, let's do this one. We're doing this one now. Okay. So again, replace all the x and the y values. Start with that. Start with the basic formula in terms of x and y. Then swap the x and y variables. Then you're going to get this all alone. So I'm adding 1 to both sides. I just like to have y on the left side. Then what's going on here? This y is being cubed. So the only way I can get rid of that cube is to cube root it, which means I have to cube root both sides, which means y is equal to cube root of x plus 1. And I forgot one last thing. You've got to convert it back to an inverse formula. And it looks like that. And I'm just going to answer this text. So f, the inverse formula is cube root of x plus 1. All right, sorry. Let's go to the next one. So again, yeah, and that's fairly important to end it with that inverse formula. So again, I'm going to start by replacing my x's and y's, like that, then swapping them. I got to answer this, sorry. It's important. And now I've got to isolate y. Now this is interesting because that's a bracket. That's the first time we've seen a bracket. And in BEDMAS, brackets come first. And in reverse BEDMAS, we have subtraction, addition, division, multiplication, and brackets, and then exponents. So that means there's no subtract. You might say, oh, well, there is subtraction and addition. But that's inside the bracket. That's why sometimes I say move out from in. So actually, the first thing that's being done to y here, outside of the bracket, is being multiplied by minus 2. So we have to divide both sides by minus 2. This is a plus x, by the way. So I get y plus 5 is equal to x over minus 2, which is the same as saying minus 1/2 times x. And then I have to subtract 5. And then I have to go back and write the inverse equation of m of x is equal to minus 1/2 x minus 5. And there you go. And notice that this technically is a line. It just doesn't look like it, because if it might have been smarter for us to expand that, because really this is the line, minus 2x plus 10, right? And you might say that doesn't look anything like that, but you'll see if you work with that, it indeed is. And notice the slope of this is minus 2, and the slope of this is minus 1 over 2. It was just a tricky way of writing a line. Okay, determine a function is defined as this, and it looks like a parabola. And notice you can see a lot in that parabola. Go back to studying your parabolas and learning what vertex format is, because this is vertex format, and I can tell you the vertex is 3, 1. Therefore, the inverse vertex will be 1, 3. I also can tell you the domain of this parabola will be dictated by the 3. So y, since it's facing upwards, is y is bigger or equal to 3, which means the domain, sorry, I should have said the original, the range is y is bigger or equal to 1. My bad, that's the original, which means in this one, the x is going to be bigger or equal to 1. So when it flips on its side, the x will only go down to 1 when x is 1. So that's good to know. Determine the equation for the inverse of this. Okay, we'll start by writing this in this format. Y is equal to x. And then swap their x and their y. So you get x is equal to 4, y minus 3. That's a 3 squared plus 1. Lots going on here. How do I get my y all alone? Well, it's got a bracket and an exponent, a multiplier, and a addition. And in reverse, bedmass, we got to get rid of the addition first. So you get x minus 1 is equal to 4 times y minus 3 squared. Now we have an exponent, a bracket, and a multiplier, and in reverse, we get rid of the multiplier first. So suddenly I'm left with y minus 3 squared is equal to, and how can, I'm going to write this in something a little bit, I'll keep it like that actually, x minus 1 over 4. Okay. And now how do I get rid of that square? I'm almost inside the brackets. How do I get rid of that square? I have to square root both sides. Square root both sides. And here's an important distinction. We have to add a plus or minus now. We have to add a plus or minus, because when you square root something and you're not working with something that's always positive like area, you must now say is equal to the plus or minus x minus 1. And that's because there are two possible solutions. Minus 3 squared will equal 9, and 3 squared is equal to 9. When we take a square root of 9 and we say the only possible answer is 3, that is not correct. We have to say, oh, it's plus or minus 3. Okay, so I'm left with this. And now I've just got y minus 3 is equal to this plus or minus square root mess. So now all I have to do now is resolve the brackets. Now that I've cleared everything else away, I just add 3 to both sides. And I'm left with y is equal to plus or minus square root x minus 1 over 4. And then finally plus 3. And now the last step, I've got to take g of x, and I've got to say the inverse formula of g of x is equal to all of this. And there you go. So your teacher probably won't want you writing in y by grade 12 functions. He wants to see everything in function notation. So determine the equation for g of x. We did. Solve for y in the equation for the inverse. Solve for y in the equation for the inverse of g of x. What does that mean? Solve for y. Is there something I'm missing here? Solve for y. I don't know what he means by that, but it doesn't matter. Graph its inverse using graphing technology, so that's essentially saying you can use Desmos. At what points do the graphs in G and its inverse intersect? Oh, that's an interesting thing, by the way. The graph will reveal it, but anytime you have two formulas, if you make the two formulas equal each other, and it has a solvable x value, that x value is where they meet. It won't work for cubics, but it will work for parabolas because you can only have two possible answers. See, parabolas can either meet in two spots, no spots, but they can also meet in one spot, and that will occur when the vertex touches the line of the parabola once. So that means you can solve any of those situations. If it's not solvable, they don't ever meet. But in this case, they're letting us use graphing technologies. State the restrictions. I already did before by discovering what the vertex was. Suppose the domain of this is that, is the inverse of function. Well, no, the inverse is, well, it might be actually, that might be half of a parabola because the normal inverse is not a function. So let's do that. Let's do 4x minus 3 squared, and we'll let Desmos do the work for us. Y is equal to 4x minus 3 squared plus 1. So there's the vertex. Now we're just going to put x where I see, and it'll draw the inverse for us. And there we can see, oh my bad, yeah, you can actually have multiple, more than 2. You can have 4. So it actually wouldn't be solvable. It might be, actually. It still might be. So it'll give you 4 possible intersections. And then finally it said if we limit the domain to the first one to that, well, the other one, so 2 to 5. No, because you can see that it will still not pass the 2 to 5, right? Yeah. It's still, if you turn that little tiny bit sideways, you're still not going to pass the vertical line test there. Had they made it from the vertex, let's say 3 to 5, yeah, the inverse of that one is going to be a function. But as soon as I go to 2, no. I think they were actually aiming for 3, and they might have done a typo. Because now that's just half the parabola. And if you flip that on its side, it will still be half a parabola. Okay, back to the textbook. So we got some extensions that I probably won't do. So here we go. A student writes the inverse of this is that. Explain why this statement is not true. Okay. So first of all, ask yourself, what kind of function is this? It is a root function, and it has been translated 2 to the left, and it's been reflected in the x-axis. So normally a root function would go from 0 to 0. But because it's translated 2 to the left, it goes now from minus 2 to 0 and goes that way. And also, this minus reflects it in the x-axis. So now it's going like that. And that's its beginning. And it's not counting the black part anymore. So it goes from minus 2, 0 down like that. Now ask yourself, is that a function? Right. What would the reverse look like? It would be just a half parabola like that. Right, standing up, going through 0, minus 2. So it'd be probably actually down here, like that. Now ask yourself what this is. Well, that's a parabola. The inverse of a root function cannot be a parabola because it's only got half a parabola there. You have to still restrict the domain and range. Now algebraically, if you solve this algebraically without using the logic, then yeah, you'll get this formula. But that is not the correct answer. In this case, you'd have to restrict the domain the same way that this one's, you'd have to restrict the range the same way this one's domain is restricted. So this one has domain and range restrictions of x must be bigger or equal to minus 2, and y must be smaller or equal to 0. That's this one, which is the original. Which means the domain of this must be restricted to x must be smaller or equal to 0, and y must be bigger or equal to minus 2. It must have the same inverse domain ranges. And if you write this equation and add these two restrictions, then yes, that will work so long as you keep those restrictions. But algebraically, no, that does not produce the response you want. Do you have to restrict either domain or range in the function of this to make its inverse a function? Yes, I just explained all that. You do indeed have to recognize the function you're working with so that when you inverse it, you do not break the rules of what existed before. You can't suddenly fabricate a new part of the function that never existed in the original. John and Katie are discussing inverse relations. John says a function is a rule, and the inverse is the rule performed in reverse order with opposite operations, sort of. For example, suppose that you cube a number, divide by 4 and add 2. The inverse is found by subtracting 2, multiplying 4, and taking the cube root. It's true, but only if it doesn't disobey things like brackets and whatever. It is true. But it's not always true, as we just saw. For instance, the cube roots will work because they preserve positive and negatives. Cube roots can be positive or negative. But as we saw from this one, squaring it produces some parts of a new function that we don't necessarily want. So he's right, but he's wrong. You have to be aware of your original function. Extending. If f of x is an interesting function because it's its own inverse, can you find 3 more functions? Yeah, we just did that. Y is equal to minus. So y is equal to minus x, we discovered, is inverse of its own function. Y is equal to 1 over x is inverse to its own function. And what else would there be? Probably be a parabola that's sort of leaning function that's perfectly reflected here, there. I don't know if I could find a third. I'm sure I could, just not think of it. The inverse relationship of function is also a function if the original function passes the horizontal line test. Yes. Explain why this is true. Well, let's say you take a parabola, and you know it passes the vertical line test, right? If you want to know if its inverse will pass the vertical line test, just do a horizontal line test. Draw a horizontal line through it. And if it doesn't, if it passes through 2 points, you know that the inverse, of course, will not pass the vertical line test. This makes perfect sense because when you're testing the inverse, this is a line of like y is equal to 5, and when you inverse that, it becomes a line x is equal to 5. It becomes a horizontal line becomes a vertical line on the vertical line test of inverses. So essentially a horizontal line, when you inverse it, becomes a vertical line. So yes, before you ever draw it, you can see if the original function passes the horizontal line test to see if its inverse will pass the vertical line test. That's the end of that. I actually think inverse functions are a great thing to study as opposed to some of the stuff you will do in functions 12.